Somebody had to open for me that door.
Next time,
So-
call me. Just call me.
Okay.
Or so you can, yeah? Just chat on Slack, help, help. Okay. Wonderful. All right, well, welcome to the third week of the course to become a millionaire. Great. Today we will continue with the notebook we were doing the other day, and we will talk about 5 important things. A bit of chatbots, so you have a feeling of how much you want to do chatbots. Yes? Or you can start thinking about ideas about chatbots. I will explain 20 minutes the basics of chatbots and why it's important. We'll talk about data visualization. I will teach you why data visualization is important. We will continue the slides. The other day you learned about predictive analytics. Yes? Prescriptive analytics. And what was the other one missing? Predictive, prescriptive, and descriptive. Yeah, descriptive is the basic one when you don't know what's going on. Predictive is when you make a model, and prescriptive is when you change something in the business. Like take this medicine or something. So we will continue with that. We will continue the notebook Python. Did you like the notebook Python? Useful? So this is the new way to do science, data science today. Mixing code and data together and explanation. And we will talk about the quiz that we will have next week. Sounds good? Excellent. For the new people, there's a Slack channel called, which is there, I think, hold on, ITCO601 at slack.com. Jimpy, can you see it? No, it's invisible, right? This is a Slack, so I will send you later the invite. I see you're not very active on Slack. Like nobody asks lots of questions.
Well, we are just watching if there's any updates.
Don't be shy to ask questions, please. Okay? Like I'll show you the Slack of other courses. Everybody is talking and commenting and sending links in the class and blah 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 and sharing. Yeah. So this is the computer graphics slide. Sir, blah blah. We want to go to the match. Okay, fine. So don't be shy to ask questions there. Like the security, blah blah blah. It's Slack. Somebody will go to help you. Sounds good? Excellent. So just a quick recap. The other day we saw the difference between descriptive, predictive, and prescriptive. Yeah, can somebody tell me the difference? Yes. This is gonna be a question in the exam, so you better get it. Srika. Jumana.
Yeah.
Who wants an A? Yes.
She doesn't want the.
You still want the A or not?
Yes.
Okay, what's descriptive analytics? There are 3 types inside descriptive, but it's basic for. Yeah. Yeah. That's it. Mm-hmm. Okay. What about causal research? What's that? Causal research.
To be aware of the problem. Exactly. Like what is exactly the problem beyond?
Or to find out the
Yep.
It's an identified or defined problem.
Relationships. Yeah. Yeah. Okay. Then we saw ways to collect data, active and passive. You saw about A/B testing. Yes.
Yeah.
You saw surveys, the problems of surveys. Mobile surveys, very good. You show an example of a couple of apps. Net Promoter Score. What's the Net Promoter Score? No. What? What's the Net Promoter Score? We calculated the Net Promoter Score of this Slack in this class, which was 0, which means
There's not going to be more promoters.
The creators.
the word of mouth is not going to be great. It's going to be neutral. Not good, but not bad. Yes? So if we don't do anything, nobody will. The users of Slack among your friends will not increase because you are not, because the score is 0. Yes? Great. La la la. Very good. All right. Awesome. So that was what we did last year, and now we're gonna talk about something very
So there's 3 types of collecting data, passive and
active. Yes. What?
the typical something is watching. This is collecting also.
A survey. A survey is active because you ask people. Passive would be check the scanner data, for example. You don't do anything extra to collect the data. Does that make sense? Yeah. So in Humana School, if they ask the students, are you happy with your grade? That's active, right? If they analyze just the grades that they already have, that's passive. Yeah? Sounds good? Okay, descriptive. So here you have an example of predictive analytics. The best school in the world to learn predictive analytics is called Wharton School in Pennsylvania. They are the best. And they developed this model. So we're gonna do a very quick exercise about predictive analytics. So for example, are you familiar with this curve? Price and quantity. Yes? The more the price of a product, the less the quantity you will sell, right? Yes? Something like that. So usually it's something like that. Yes? Yes? So imagine I collect a few data points. I do some experiment and I place the product at $10, $20, and $30. And this is the points I collected. Yes? Let's say this is 10K products and this is 20K products. Okay? Predictive analytics would be how much will I sell if I place the product at $5? Right? Here. What do you think?
I think more.
More. Give me a number. In this class, numbers.
Okay.
30K.
30K? 30 is around here. Anybody else? 35. 30. Jumana. How much?
If we increase it by 10?
No, if we reduce the price to 5, how much we will sell? How much? 40. Who gives more?
Above 35 to 40.
35 to 40.
And 40 also.
All right. So anyway, predictive analytics is making a model. And, it's like 25. Okay.
No.
No, it's not.
I'm sorry, this is the model I made.
35.
What? You're not happy?
25?
What? it's there. What were you thinking? Yeah.
That when we reduce the price by 10, they should push to almost double.
This increased by 5 here.
Okay, well, I made a linear model, right? My linear model, can somebody give me the equation? Y is, so this is, the quantity I will sell is,
Right?
it's something that depends on P. Yeah, it's a function of P, right? And in this case, if I do a linear model, it's a straight line, no? So I could
Yes.
put the equation of the straight line, which is could be, I think it's 1 minus P. Yes, I like it. Divide by, intercept is going to be about 40 multiplied by 35, something like that. Is that correct? That would be the equation of this line here, right? And this is a linear model.
From where you got the 35?
35 is the price when P is 0.
No, it was 25, you said.
P, well, it's wrong. So, do you want to find the formula? Oh, this one is wrong. It should be
I think P minus
P minus 1, right?
Yeah.
Thank you very much. Bonus point for you. Something like that. Here.
35 and 35, they will cancel each other.
No, you always have one.
Yes.
If one.
When P is 35, this is 0. It's correct. When P is 0, this is wrong. When P is 0, this is
Minus.
When we
P minus 35.
I'm gonna make it again. We make the line passing by 0 with the slope we want. What is the slope here? It's 35 here and 25 here, we said, yeah? So the slope is 35 here and 25 here, right? This is the definition of the slope. So for every 35, we move 25 down, right? So it's minus 25 divided by 35. This is the slope. Is that correct? Kind of? Yes or no? No? And here I put the variable here, which is P. When P is 0, I'm here, right? When P is 1, I don't know where. But when P is 35, I'm in minus 25. Which is correct, yes? And now I have to move this slope up by how much?
25.
By 25. Thank you. If you rearrange this becomes 25, 1 minus P divided by 35. Yes? But it's clear like that. So this is usually called A, and this is called B, but it doesn't matter. Well, anyway, it doesn't matter. It's a linear model. But you were thinking about exponential model or something like that, right? Which is more realistic. So this is the problem with prescriptive analytics. You make a model with your data, but outside the data, usually it's not valid. So you have to be careful. You have to be careful predicting students that will come and so on. Sometimes the data here is wrong also. So you have to be careful with that. How much you trust the data? Yes? Okay, well that's an exercise. An example of prescriptive analytics. Another exercise of prescriptive analytics. Sorry, predictive analytics. here you have a table. It's an example from America. In America, you know, the museums, they don't get money from the government. Do you know that? It's all donations. So every museum employs like 20, 30 people, and their full-time job is to call rich people asking for money. Yeah. Which is tax deductible. But yeah. Really. This is real. Crazy content. So this exercise is about, imagine there is a company and they have potential donors on a mailing list. This is before the internet. And you know, they will send a mailing letter like, hey, we love your support, and are you going to give us money next year also? But to send this letter is expensive. So it would be good if they send it to the people that are most likely to give, instead of sending it to me, that I'm poor and I don't have money to give, right? So here you have some data of, these are customers. And this is year 1, 2, 3, 4, 5, 6, 7. And we want to predict.
If they will get money or not.
Correct. And 1 means the guy donated money, or the woman.
That means if they
0 means they didn't donate anything. Okay? Okay, good. So how would you model this data to know how many ones I'm going to have in 2002, 2003, 4, 5, and 6? I give you 1 minute to think about it. Starting now.
You can see.
How many ones I'm going to have for each customer from 2002 to 2006. 1 minute to think about it.
I can count the numbers in 1 minute.
One, you need to count it. You need to tell me what you would do.
From all the IDs?
From all the ideas, yeah.
Hmm?
Yeah.
The one who they work, maybe he.
Okay, but we don't have this information. We only have information about they gave money or not. Shaima?
Yeah?
Shaima? Aisha, sorry. What are you doing? Are you counting?
No, I was predicting.
Very good. Because it's predictive analytics. Very good. Think about it. Can you find some rule or something?
I think yes, like you can see the first rule, second rule, third rule, like just like linear, 1 yes, 1 no.
Yes.
Yeah, using classifier. That's good.
I love it.
We cannot predict.
And that okay.
شوفوا الرولز هذا.
Okay, يعني بس prediction will not be
Accurate. That's
right
right.
when prediction. التوقع ما يزيد ما ينقص.
Well,
Yes, for more realizing.
whoever gives the best answer gets the candy. So, yes, Chimpit.
Actually, the first one.
What rule or what model would you do here? Okay. Yes. No? Somebody else has some idea? Yes. Jumana. This is great for schools, by the way, also. It applies to parents.
Yeah, so if we observe the pattern, it says that the first three students have the same pattern.
Yeah.
That they only donate once and then no. So we will expect to continue no for.
Okay, you're saying this is a very common. Interesting. You found a pattern. You could look for patterns. Good. Yes, somebody else? Dula?
This pattern is for four students.
Oh, it was the same.
First.
That's very good. That's very good. The problem, Jumana, that's very nice. But what if I have a 1 here and then a 0 here? What do I do here?
One.
Really?
One here is 0 and the other is 0. The other is 0.
Majority. Nice.
The date she gave previous yes or no. According to
Zika, what would you do?
I would feed this data to a classifier.
What's a classifier?
Classifier is something which uses some kind of rules, and based on these features, I'll take each year's data as a feature, and I'll try to predict if they're going to donate the next year or not.
Okay, let's see. So you would take all these people that are the same, 1, 2, 3, 4, right? Look at all these people that are the same and call them group A. And then what? And then you would look, you would add these numbers here,
Yes.
and you would do the average or something, or what would
No, what I would do is I would use each year as a feature, whether they have donated or not, and then I try to build a model which predicts for the year 2002, which will take all the remaining columns as features.
That's pretty good.
So I would use the data, say we have like 100 rows, I split the data in sets of 10, and then I try to use the 90 and take it on the 10. I do all possibilities to get the maximized model, and I will use that model to predict for 2002.
Did you understand what he said? Yes? Yes? But basically what you're doing is the same as grouping people.
Yes.
Maybe there's another big group of people with a different pattern, and whatever, we have 5 years, so that we have 32 groups, no? Because we have 5 years. Maximum we have 32 groups. And then you will calculate, oh, group A, this group donates 2.1 times, and this group 3.1 times. And so you have a new user and say, oh, you belong to this group, so you are going to, yes? Does that make sense? Does that make sense? Jumana? Yes.
But still, we cannot generalize it.
Why not?
Yeah, we cannot generalize it. Something might happen. Maybe even one of these students, group A, then he changed his mind and then he donated. So he will be not in group A.
The same problem as a school.
Yes.
These are subjective to change.
That's why it's called probability. So you can, yes.
So you're basically clustering the users into various groups, and if a new user comes, you're putting it to the maximum group, the nearest group that he might belong to, and then based on that you're predicting whether he will donate or not, right?
So Jumana, we only have this data. You don't have any other data from the persons. So that's the best thing you can do. Look at what these same kind of people did in the past,
Yeah, based on their history.
right? That's the best thing you can do. Does that make
Okay.
sense? Yes.
So when a new user comes, you see how a past user, similar to this user, you're basically using the past user's information to predict, right?
Yeah, I think so. You would look at the past history 10 years ago and see, okay, when I see this pattern, what does he usually do, this kind of user, this kind of pattern, yes? Does that make sense? Abdullah, no? Yes.
It's still not clear for me.
No? So, I would Very interesting to learn. Look at this. Donate, and then no. Right?
5 years.
And we want to know what will happen here. Yes? Okay, fine. So you can take this data as training. And say, look, 1, 0, this. 1, 0, this. 1, 0, this. 1, 0, how much here? 1, 2, 3, 4. Total of these 4 people? 4. From here to here, right?
Right. It's
Interesting. So imagine I'm here, and I see 1, 0. What's the historical average I've seen before? 4 donations divided by 4 people is 1. So the average I expect is 1. That's the best thing you can say. Yes? Does that make sense? If you decide to do it like that. 1, 1, 1, 2, 3, 1, 1, 1, 1. And you count and see, wow, 1, 1, 1, 1, 2, 3, 4, 5. Total, 5 plus 2 plus 3, 10. Dividing 3, 3.3, right? So you can see, and you come here and say, oh, 1, 1, what do you expect to see? On average, I will see 3.3. Yes? That is if you choose to predict the future here using the last 2 years. Yes? Makes sense? So in this case, we look at the history, we look at 2 years only, we look at the next 4 years and say, wow, this is what happened. So, yes? So in this case, we could be able to do 4 groups. Yes?
1, 2, 3, 4 years.
Why we don't take the first 4 years?
You could take more years, right? You could try to predict with 3 years.
In 19th century, so maybe I think it's better to take us to
Yes. What's the question again?
you said we take just 2 years, the first 2 years.
Yeah.
1995 and 1996.
For example, yeah. Well, we can take 1 more year, right?
Yeah.
And then it's more precise, right? Because we have more information, right? And if we had more years, we could look at more years, and then we can make more groups. Does that make sense?
But for this problem, do you think it makes sense to have more weight for the recent years? Or
The more, okay, that's very interesting. So here's the question.
because if someone has recently donated, there might be a high chance that he might donate again.
Very good, Srikant. We will see this soon. Okay? Very good. So, for example, look at Bob. Bob donated. Let's imagine we have this data from Bob, okay? And that you had training data. What do you think Bob will donate in the next?
1, 1, 1, 1, 1.
Everybody agrees?
Yeah.
Okay, interesting. What about Sarah? What do you think Sarah will do?
Will be 1 and 0, 0, 0.
What about Mary? What do you think she will do?
Go.
1, 0, 1, 0, 1, 1.
We need 2 more zeros.
Crazy.
It's not like a pattern, okay? Though maybe some people have patterns, I don't know. Okay, so I think everybody realized that there's a thing called, if he donated recently, it's more likely he will donate, right? So, so for example, what about here? Look at Mari and look at Shamila. Look at Mari and look at Shamila. How many times did Mary donate?
5,
5. And Shamila?
6.
That's the average. That's the average in the last years, right?
Okay.
But who donated in the last year?
Mary.
Okay, good. So Shamila donated more on average, but she didn't donate in the last year. And Mary, on average, donated less.
But she donated last.
Okay, so who do you think is more valuable now as a future customer? Mary? Who says Mary? Raise your hand. And who says Sharmila?
I think it's Shamila.
You say Sharmila? Okay, people who said Mary, you can take a sweet from the box.
Yeah.
Thank you.
You can pass it. Very good. Yeah, so let's see.
Why?
Why is that? So there's a thing called recency. Recency, which means recency, yeah?
Frequency.
Yeah, so recency means when is the last time you donated? Is it a long time ago or not? Yes? Then you have the frequency, and the frequency is how many times you donated in the last 10 years or 5 years. So it turns out that for customers, recency is more important, way more important than frequency.
Ah, okay.
Why is that?
It's human nature. Like, if you didn't go to the gym for the past 4 days, most probably you didn't go to gym.
Thank you. Okay, so there's a thing called death. Some customers die physically, but also they die as a customer because they are fed up, or they find a better place, or they change cities or schools, and they will never come back. And that's way more important than the frequency. That's why, because people die. That's the reason. Does it make sense? Speak up. What?
I think recency is you needed a new information.
The problem is customers die, and when
It's
they
close-
die,
it's close to
once they're dead, they will never come back. So you have a lot of zeros forever, and that's very strong in the statistics. Does it make sense? Let's review very quickly what is conditional probability, which is what we are calculating here. Yeah, are you familiar with this notation? You saw it in high school, yeah? Are you familiar also with the Monty Hall problem? Here it is. Let's watch it very quickly. The Monty Hall problem is to check if you understand conditional probability. Let's see if it's in. Can we see projector? No. Projector. Oh no. Okay.
Wait, the projector will start up momentarily.
Oh. One second. Okay, good. So the sound is not coming. So what I'm going to do is to
car and day. Are you gonna stay with your choice, or are you
Can
gonna
you
make
see?
that leap to something different? And very often contestants would stand there agonized, right? So they've got some new popular show back in the day. Contestants would go on this game show and maybe go home with the car of their dreams. First of all, the game show host was a very famous guy named Monty Hall. And Monty would come onto the show and he would have 3 doors. And a contestant, that's you, would come onto the show. Monty would give you the chance to choose door number 1, door number 2, or door number 3. Now behind one of those doors, only one, was your dream flash car. Bright red, sports car, very fast, it was awesome. And behind the other 2 doors were zombies. That was the let's make a deal word for something that you don't really want. So you had like a 1 in 3 chance of getting your dream car. So suppose you pick door number 1. And
Which door do you pick? It doesn't matter, right?
Monty would then do the same thing every week. He would go over to the 2 doors you didn't pick, 2 and 3, and he would open one of them. Let's suppose he opened door number 2. And the door that Monty opened would always have behind it a zombie.
So he knew.
Well, he knows everything, right? He's the game show host. And then Monty looked at you in the face and said, do you like door number 1, or do you want to switch?
Do you switch or do you keep your door? Who keeps the door? Who switches? Who switches? Who doesn't do anything? Doing nothing is keeping the first door, by the way. Who keeps the door? Does nothing. And who switches? Okay, nobody gets candies this time. Or let's see why.
Doors
I
open.
think one more switch too, in this case it's door.
Excuse me?
Maybe.
If I keep it, I have more.
If you keep it, you have more?
Yeah, maybe 1 or 2 possible to get the car, right?
I don't
If
know.
I switch, maybe
Switch is bad. Changing is bad. You already chose 1. Why switch? That's right? Right.
Door number 3, are you gonna stay with your choice, or are you gonna make that leap to something different? And very often contestants would stand there agonized, right? So they've got some new information,
So stick or switch.
stick or switch. Well, a remarkable thing about this problem, as simple as it is that it sparked just endless debate. In the time of the show, I don't recall anybody ever saying there was a dedicated strategy that you should always follow. But in fact, there is a dedicated strategy you should follow. You should pick door number 3. That's the answer. You should switch.
Nobody gets candy.
Number 3. Maybe.
Excuse me? You changed your mind now?
No, from the beginning she chose number 3. Yeah, and then he asked her to switch.
No, you choose 1 door, which happens to be number 1. The guy opens one of the other 2, and he always opens one where there is not the car. Now you have new information. Do you switch or not?
No.
Really?
Switch. You should switch every time, and that will do the best for you over the long run. So there is a 1/3 chance that the car is behind the door you picked.
Do you agree with that?
Yeah.
Yes?
What's the chance? Yeah.
1/3 chance.
Yes, there are only 3 doors.
Hey, don't cry. Hey, no crying in this class.
Initially. That means there must be a 2/3 chance, much greater, twice as big. The car.
Is this correct? Everybody agrees with this truth? Srikan. Yes?
Yes, since there are 3 doors, the chance is 1/3 on the door I pick
And 2/3
for the
correct. Yes?
Car is somewhere else, and since we know that somewhere else cannot be door number 2, because when it shows that, it's got to be over here. And this is what you should choose. You should switch. Twice as likely to have the car be.
Let's watch it
Gotta
again.
be over
Whoop!
here. And since we know that somewhere else cannot be door number 2, because when it shows that, it's got to be over here. So this is what you should choose.
So now the goat or the car has not disappeared, right? So it's either in your door or the other door, right? Your door has 1/3, and not your door has 2/3 still, right? And they show you from these 2/3, it's not here. So the
So
other
now equal, 1/3,
1/3, 1/3. That's not probability. Probability is always 1.
Yeah, I know. But after we know that already got that it's here.
Is
so-
1/3, 2/3.
Yeah, 2/3. Yeah, because it's everybody.
It's just double. So you should switch. You should switch. What's the thing is that the guy always opens the car where the door where the car is not there. If he opened a random door, it doesn't matter. But he's not opening a random door. He's opening the door where the car is never there. That's the thing. Does it make sense?
But in my point of view,
Yes.
how will I know there's two doors in front of me, one is open? How will I know this have 2/3 and this have 1/3? If
By
somebody
studying
comes in and they say,
this
"Will
course."
you change?" I would expect that the car is in the door that I chose. So of course I'm not
You can
changing.
ask her at the end of the term.
Sure? What?
Nothing. Go. Explain. Ask the question again.
So
Aisha.
which, as I said, there are two doors.
There are 2 doors left.
One is open. How will I know which one is 1/3, which one is 2/3? In my point of view, I don't know. I'm just guessing.
Very good. Do you want to learn this?
Yeah.
Okay, let's watch.
You should switch. Twice as likely to have the car behind the door that you didn't pick as the door that you did. 2/3 probability to a 1/3 probability. Now, if you switch, are you guaranteed to win? Absolutely not. But if you play this game over and over again, on average, you will win 2/3 of the time. So switch is your strategy, and you can't predict. One thing that you might say is that the initial 2/3 chance that the cars behind door number 2 and door number 3 got concentrated behind the door that Monty did not open. That's effectively what's happening. That's intuitively what's happening. And that, in fact,
Do you believe that, Aisha? Not really.
is what the mathematics shows is happening. Now, there is a way to see that in kind of a more grand way. We imagine not having 3 doors, but we imagine having 100 doors. And let's imagine that we're playing the same kind of game. We have Monty over
Aisha, same game. Now there is 100 doors.
here. He is going to give you an
Yeah, what needs to do here?
opportunity to pick a door and read flashcards behind one of these 100 doors. But there are 99 zones on the other doors. Now, what is it that you're going to do? Well, you're going to pick a door. Say again, you pick door number 1. Now, you're feeling a little bit different than you might have felt in the case where there were 3 doors, because there you thought, wow, I've got a 1 in 3 chance. Here you're thinking, I've got a 1 in 100 chance. I'm not going to do
Is this
it.
correct? A priori you get 1 in 100, yeah?
It's not behind door number 1, it's probably behind.
And that's the probability that the car is not in your door.
Yeah.
99 in 100, yes, correct? But now what?
And one of the other 99 doors. What Monty does is he opens 98 of those 99 doors. He shows you 98 zonks, and he asks you now, do you want to switch?
Aisha, you switch?
Yes, I switch.
Oh, yes. Give her 1 candle. Why? It's this. You took? It's the same, right?
I knew I wouldn't switch.
Wait.
Well, maybe just because of the sheer numbers, this thing is a little clearer. You know that there was 99 out of 100 chance that the car was over here, and now the only door you're left with after Monty shows you all those zonks is door, say, number 37, and you're thinking, this is no good, all those doors are no good. Do I want to stay with 1 or do I want to stay with 37? You can sort of almost feel the concentration of that 99% going behind door number 37, and so you switch over here, and very likely you're going to right away.
I'd like to clap for
Well, thank you.
Yes? This makes sense. That's an example of a priori probability and conditional probability or posteriori probability. Yes? Okay, it's also known as the Monty Hall problem. Very good. Beautiful. And we express it like that, A dash B, right? A dash, I open 99 doors is probability that the car is in this door, given I open 99 doors, is 99%. Or 2/3 or whatever. Yes? Okay, just a very quick review. Humans are really bad at probability because it's not intuitive. When the lion is chasing you, you don't have time to think probability, but it's good to know. Right. So back to the recency frequency, and this will help you understand this now. So here is this predictive model called recency frequency, and we will count the number of people in each combination. It's kind of a clustering, right? A bit more simple than the clustering you were proposing, but well, let's see. So this is what we can do. We can count the recency and the frequency numbers for a few players, right? So for example, Bob, recency here is 6, and we put a 6 if he donated in the last year. Okay, it's a bit weird, but that's this. Sorry, recency 6 if he donated. So for example, here is 0 because he donated in 1995, which is assigned as 0. So if you donated in the last year, recency is 6. If you donated 1 year ago, it's 5. If you donated 6 years ago, it's 0. Does that make sense? Yeah? Frequency is the times count. It's count, right? Is that clear? For example, here 4, no?
You're talking about
1, 2, 3.
Just the last year. Mary's recency is
4.
it should be 1, 0, 1, 0,
1, 2, 3. Oh, yes. There's a year which I'm not counting, which I think is year 1995, I think. 90, this one, they are not counting it, correct?
The last.
This one, they are not counting it. So here, 1, 2, 3, 4.
5.
Yes, correct? So frequency is,
7.
yeah, is the count from 96 to 2001. And recency is the index of the year, but reversed. So 0 if he donated in no year, and 5 if he donated in 2000, 4 if he donated, we don't have a case for 4. But yes, makes sense? So recency is the maximum value, which is 6 if you donated in the last year. If there's a 0 between now and the last year, you donated, it's 1 less, 1 less, 1 less, 1 less. Yes? Okay, so with these two numbers only, the frequency and the recency, you can check this. And here you have the repeated transactions, yeah? So basically the recency, this is the recency here. And what do you have? So here I put the recency, yes? So Sarah would be here. And what do you see? And this is the count of donations that they gave in the following 4 years, right? So which is the highest number? For recency, 6, right? Does that make sense? Interesting.
Oh,
Yeah. So recency 6 means they gave money the last year, the most recent year. So for people that gave money the most recent year, the following 4 years, they gave an average of 3.75.
How did they calculate the 3.75?
They have some training data. Yes. Look at people that didn't donate the last year. Sorry. Yes, that didn't donate the last year. What happened? This is the last year of transaction, right? So people where the 2001 didn't donate, so they stop at 2000, yeah? The next 4 years, 1.8. People that have a 0, not in the last year, but earlier, yes? In any of the previous years, they donate much more, right? So here you have people with the same frequency, but the recency is much more important, right? You see it? Yes? If you donated the last year, it's like 1.5 times more. So same frequency, both donated 5 times, but if you donated the last year, wow, it's the next 4 years you donate much more. That's a huge difference. Does that make sense? The same for these guys. The guys that donated on average 4 times between if you didn't donate in the last 2 years, the next 4 years, what's the average? 0.5, which is like you're dead on. But if you donated the last year, wow, it's better than people that on average donated more, right? So what do you see in this model? Recency more important than frequency. And why is that? Because people die as customers. I love this. Does that make sense? I want you to take a look. Let's see. Yes. Very good. Okay, so actually, they develop a model. Conditional expectations. So this is the last year of transaction. So this means these guys stopped donating a long time ago, right? In 95. These guys donated the last year, yes? And here we plot the repeat transactions, so the frequency, yes? In the 4 following years, actually 5, but 4 following years. So this is the model that they developed using this simple table, and this is the reality, what actually happened. Sounds good? Pretty accurate, yeah? So no need to make a super complicated clustering.
Yeah.
But it would work, but you don't understand why,
Right.
which kind of,
And these two are like aggregate of all the columns.
yes, correct. So it's a way to cluster. Recency frequency is a way to, you can see it as features, and then you can do a model about it.
Instead of giving all the raw. So
So-
they do this model before in 1995, and then see as the years come by and see if the model they predicted was accurate
Uh-huh.
after the actual things came out.
Yeah. Okay. Here you have the same kind of information. And this is the probability that you will have, the customer will have some interaction in the next years. And here you have the recency, so which is the last time they were active, right? And here you have the number of transactions. And what's expected is like, okay, so people that donated the last year, yes, well, higher probability, right? And for example, these guys here donated the last year and all the previous 19 years. So probability is 3.94. It's very high, right? For the next 4 years, 4.2 years, very high, yes? So it's a guys that always donated, right? And here you have the guys who skip 1 year. And if they skip the last year, 1.48, and if they skip this year, is 3.73, right? So recency again, it's the same information. But look at here now. This is a guy that never donated, and never, okay? Because 0 transactions. These are the guys that never donated, yes, never. A random dude, okay? Never bought a CD in CD Now. Do you remember CD Now, this website? It was before Amazon, okay? Before Amazon sold CDs, there was a website called CD Now, and they had that, as I said. So customers that never bought a CD in the website, never, the probability that the next 4 years they would buy one CD is 1%. But, okay, but look here. If your customer had bought a CD 18 years ago, the probability that he would buy a CD in the next 4 years is lower
Zero.
Less than 1%.
than if
Yeah.
Why is that? It's because the survival model is because people die, right? It's the same in your phone address book. If you type a random number, the probability that somebody will answer is higher than if you type a phone number of a number that is not answering you for the last 2 years. Like some angry friend or something, right? And why is that? It's because customers die or leave. Does it make sense?
That's why the recency is important.
Speak louder.
That's why you said the recency is important than the quantity.
Yes. Way more important. Way more important. Yes. Yeah.
Doctor, what is X-TX?
TX means transactions. TX means transaction and X means year probably, but it doesn't really matter.
So if we want to predict a data, we have 2 ways. The condition, this one, and the other one which have 2 different variables and frequency.
Yes. So
which one is better?
why do we see this model here? So as Rican proposed at the beginning, you could cluster the users by
So it depends on
by year, no, and what happened, and make some complicated features. But you just need 2 features, and you will have a very good model that you can understand, that humans can understand. And this is called the recency frequency model, which has been used, by the way, it's super famous, this model, by marketeers for a long time in the 60s. Okay? Because in the 60s, there was no internet, and what do? You send catalogs to people, and they would buy from you. Remember? Catalog buying? Did anybody try that? So every year they have to make a decision, because to send a catalog costs like $20. So if I send it to Abdullah, and Abdullah doesn't buy more than $20, I lost money with you, right? So it was very important to send as much catalogs as possible, but to send it to people that would buy. And they developed this model and say, oh, this customer bought last year. Sell it. This customer, 19 years without buying. He bought one time, but now he's 19 years without buying. Or maybe he moved house, changed city, or died. Remember that people die. Like, if you have 100 people, sorry,
No, it's fine.
one will die this year. Same thing. Make sense? What time is the prayer?
It's time.
Okay, so we'll have 15 minutes prayer, and when we come back, we will talk about data visualization, and we will continue with the notebooks. So, Jumana, that's works for subscriptions to the school, for example. If you have one, and I think you can see it, no? If you have one family that stops bringing the kids, probably they move city and they will not come back. Then you can,
Applies to all companies and organizations.
yeah, and it's realizing that survival of the alive dead. stuff. So if you're gonna send a brochure, you will not send it to customers that stop being your customers. It's more, as you saw, it's more profitable to send it to unknown customers. It's so funny. Yes?
And especially those who have relatives and brothers and sisters, because they will bring more and more customers.
Mm-hmm.
Or they
Okay.
might have moved to another school.
Okay, so probably your model have some tweaks. Yes. Second, did you get the Slack?
Yes.
So
An email or something.
WhatsApp him. He likes WhatsApp, so you can WhatsApp him,
Oh.
and it's very good.怎么样？